Assalamualaikum and welcome to everyone. So we are from Group 4. We'll be present about the real-time operating system. This is our group members. So we have Hadif, Azwa, Dinas Kumar, Muhammad Noaim, Noalia Adriana, Siti Nasharina, and Muhammad Amirul Hazim. So this is the overview that will be covered in this chapter.
Assalamualaikum. We are going to talk about what is RTOS and why it's important. So, RTOS stands for Real-Time Operating System. It's a special type of operating system that is optimized for predictable and timely task execution. This means it responds to event or data immediately with minimal delay. It's especially used in systems where precision and reliability are very important, such as automotive, medical, and robotic systems. So, why do we use RTOS? It is because in critical systems, even a small delay or downtime can cause serious problems like safety hazard or system failure. So, RTOS ensure the minimal latency and maximum responsiveness, which helps the system react quickly and efficiently. So for some example of devices that use RTOS include printer, router, robots, and vehicle. So basically any device that needs a real-time performance to function properly. So next, we are looking at how an operating system works in real-time system. There are two main types, which is standalone application and complex real-time application. Standalone application usually don't need an OS. These are often embedded systems like microcontroller that perform specific tasks on their own. On the other hand, in complex real-time application, it needs an OS because they manage the multiple tasks at the same time. This system require more advanced features like handling the file system, network, and Windows. The OS helps by making sure tasks run on time and reduce the time it takes to design the software. Okay, so next, a real-time operating system is designed to manage and prioritize tasks in a way that ensure time-sensitive processes are complete on schedule. One feature is efficient scheduling, which allows the system to prioritize and manage multiple tasks, ensuring the most critical tasks are complete first. Another important feature is optimized memory management, where the RTOS allocate and deallocate memory efficiently to prevent waste resource. In addition, smart resource allocation ensure that hardware resources like CPU and memory are distributed effectively among various tasks. Robust interrupt handling is also crucial in an RTOS, as it allows the system to respond quickly to external signal or change in the environment. Finally, consideration like the size of the kernel and the overall performance of the system are also taken into account during design to ensure that the RTOS function efficiently, especially under real-time constraints. Interrupts are critical part of an RTOS as they allow the system to quickly respond to external events. The main purpose of interrupt is to schedule tasks by allowing the system to prioritize important operations based on urgency. Interrupt also serve a asynchronous notification, signaling the system to respond to events that are happening outside the regular task flow, such as user input or hardware signal. Additionally, interrupts are used to handle exception or unexpected situation that may disrupt normal system operation. Interrupt can come from hardware such as timer or sensor, which send signal to the CPU, instructing it to pay attention to certain tasks. Software interrupt also play a role allowing the system to perform specific actions such as making system calls to request service from the operating system. Last but not least from me, interrupt service routine (ISR) are specialized pieces of code that are executed in response to an interrupt. When an interrupt occurs, the ISR is triggered to handle the immediate task at hand. Typically, application runs in an infinite loop, performing background tasks. However, when an interrupt happens, the system stops the current operation to handle the foreground task, which is more urgent. Timing is absolutely critical in this routine because they handle essential operations that require precise timing to ensure that the time-sensitive process are complete exactly when needed. ISR are designed to operate quickly and efficiently to avoid delays that could affect the performance of real-time system.
For scheduling part, scheduling is a number of tasks, resource requirement, execution time, deadlines, periodic, and sporadic. Scheduling have a different algorithm that can be used for clock-driven scheduling, product-driven scheduling for RFS, CDF, LST, and weighted round-robin scheduling. For scheduling algorithm in RTOS, first, clock driven. Clock driven is a all parameter about jobs for execution time or deadline known in advance. Schedule, schedule can be computed offline or at some regular time in instance. It can be used for minimal runtime overhead and not suitable for many applications. For weighted round robin, it's a job schedule in a FIFO manner, first in, first out. Second, time quantum given to job is a proportion to its weight. For example, used for high-speed switching network and not stable for precedence constraint jobs. Like job A can run only after job B, but no point in giving time quantum to job B before job A. Next is a priority scaling. Priority scaling is a processor that never left idle when they are ready tasks. It's also allocated to process according to priorities. The priorities have a two divide by two. First, static at design time. Second, dynamic at right time. Okay. For the schedulers also called dispatcher. Schedulers are part of the kernel responsible for determining which task run next. And most scheduler most real-time kernels use priority-based scheduling, and each task is assigned priority based on in its importance. And schedulers are priority for its the priority of scheduler is application specific.
We proceed to the priority-based kernels. There are two types of it. First is non-preemptive and the second is preemptive. So for non-preemptive kernels, they perform cooperative multitasking. Each task must explicitly give up control of the CPU to maintain the illusion of concurrency. The asynchronous events are still handled by the ISR, which is Interrupt Service Routine. ISR can make a higher priority task ready to run, but ISR always return to the interrupted task. The advantages of the non-preemptive kernels. The interrupt latency is typically low. It uses non-reactive functions without fear of corruption. Task response is now given by the time of the longest task, and it less need to guard shared data through the use of semaphores. The disadvantages of non-preemptive kernels. First, responsiveness. A higher priority task might have to wait for a long time. Response times is non-deterministic, and very few commercial kernels are non-preemptive. We proceed to the preemptive kernels. The highest priority task ready to run is always given control of the CPU. If an ISR makes a high priority task ready, the higher priority task is resumed instead of the interrupted task. So most commercial real-time kernels are preemptive. The advantages of the preemptive kernels. First, execution of the highest priority task is deterministic. Then, the task level response times is minimized. The main disadvantages of non-preemptive kernels. It should not use non-reactant functions unless exclusive access to these functions is ensured.
Hello, my name is Hamazon. and I will talk about memory management in the real-time operating system. So for the real-time operating system, the real-time operating system main CPU unit often limit the amount of memory they use to ensure deterministic behavior and predictable performance, which are crucial for real-time application. So there is a few things that have to be paying attention of, such as cost, size, power, and weight constraint, because most of the main CPU for the RTOS are usually small to be implemented into the machine. Then memory control. For RTOS, it allows a fine grain memory control should be possible so that it can be used effectively, because fine grain memory control allows for precise management of memory access, enhancing system reliability and security by preventing unauthorized memory access and data corruption. In RTOS, the memory allocation is often restricted to a specific designated region of the physical memories. Usually, they avoid memory allocation into the virtual memory to avoid problem with paging and virtual memory, and the allocation is often statically and permanent, rather than the entire address space to ensure predictable and deterministic behavior. This contrasts with the general purpose of operating system that might use a virtual memory and extensive memory management technique. The real-time operating system (RTOS) prioritize deterministic behavior, which means they need to guarantee the memory operation, including allocation and deallocation that can that will happen within a predictable time limits. However, there is a general issue with the current storage management, which is heap and stack management in the memory management. I will explain it in the next slide. Okay, the first one is heap management. Heap management is one of the storage management of the RTOS. The RTOS use heap management with an allocator. An allocator will decide how much space the memory required and when the allocated space can be released. By returning allocated space may require the programmer by using a special keyword and specific function keyword such as malloc, free, or size off. This can cause an error because of human interaction. It will be more error prone. So what is the heap management? The heap management in the runtime will monitor the memory and determine when it's logically can no longer be accessed. When the memory can no longer be accessed, I'll monitor the memory and release it when it no longer being used. But there is an issue here where it can potentially disrupt or introduce an overhead in application performance. So what is an overhead? An overhead is an extra resource used to manage the memory, which can cause slow response of the system. And another one is garbage collection. Garbage collection is to prevent a memory leak by freeing up unused memory to be reused back. However, the garbage collection can cause a performance bottlenecks, unpredictable execution pause, and potentially for memory fragmentation. Next is stack management. Stack management is another one of the important memory management for embedded systems such as RTOS. The stack management can specify a stack size, which make it easier for the programmer to specify for a task or thread. However, calculating stack size is difficult because stack grow through a procedure calls. The execution of behavior must be known to be for the stack to be calculated, and it is similar to worst case execution time analysis. So the typical approach that a programmer usually do is to control the flow analysis to determine worst case stack bound. But be mindful, poor management can cause stack overflow, where the stack grow beyond its limit, which can cause a memory leak and the data corruption or crash of the system. In the context of RTOS, device management refers to the system ability to to control and interact with various hardware components connected to it, such as sensor and actuator, display and communicating interface, or other I/O. So device management are often not directly accessible in general purpose OS because in RTOS, the device management are designed for a specific time critical application, prioritizing deterministic behavior and minimal latency over general purpose features. So it is crucial for the device management to be able to access the device for a crucial task, which can cause a fatal when there is a mistake for such like hard real-time system. However, the device management in RTOS can potentially cause race collision. This happens when the multiple tasks in the RTOS try to access and modify the same hardware resource, like a specific memory location or a peripheral concurrently. This can cause a race condition where they try to access the same resource, which can cause a deadlock. So the device management in the RTOS don't prioritize real-time constraint, and they can cause race conditions, such as I said before. What is the purpose of this device management? The purpose of this device management is to produce a time, predictable, and safe system for a real-time system, such as security purposes.
So I'm going to talk about semaphores. So it is invented by Sir Dijkstra in mid 1960, and it also variably used to control access to a shared resource and also make, ensure only one task can access in a one time. So it is used for mutual exclusion, signaling the occurrence of an event and synchronized activity among tasks. So in this slide, we have two main type of semaphores, which is binary and counting. For a binary semaphore, we only have two values, which is 0 and 1. And other than that, it also can act as a log, similar to mutex. And binary semaphore is only ensure one task access a resource at a time. And the second one is counting semaphore. The value for the counting semaphore is from 0 and up, then 0, more than 0, and it also be used to control access limited number of identical resources. Next, the semaphore initialization or create. During the initialization process, the semaphore is being given time, and we assume it as 1, and it will empty all the waiting list. And for the wait, semaphore wait or pen, when the task is performed await, if the semaphore is positive value, it will decrease and the task will continue. But if 0, the task is blocked and add to the waiting list. But some system also support timeout. So if it support timeout, the task will be unblocked and the error code will return to the task. Signal or pause, in this process it will release the semaphore. If no task is waiting, the semaphore value is incremented. Otherwise, one of the waiting tasks is ready to run, the semaphore value will be the same. And next, which waiting task we receive the key. So we have two, which is highest priority waiting task, which is priority based, and first waiting task, which is first come first serve.
Okay, so for Linux, for real-time application, first of all, we can see the resource allocation. There was no support for handling priority inversion. So the become the priority inheritance is now available for preventing priority inversion. So after that, we will see the interrupt handling. It will disable the critic in the critical section of the kernel. There were no worst case bound on interrupt latency available. A device might disable interrupt for a few hundred milliseconds. Okay. For the third is the process heavyweight. The context switch takes several hundred microsecond. Okay. After that, and lastly is the processes were not preemptible in kernel mode. So system calls like fork take a lot of time. High priority thread might wait for a low priority thread to complete its system. This is the existing real-time operation system. It will best known and widely used. We can see Lin OS, VxWorks, OSE, Windows CE, and RT Linux.
Okay, hi everyone. I'm Dinesh Kumar. So I would like to talk about existing RTOS, best known and widely used. So there are many of the examples, such as LYNX OS, OSE, RT Linux, VxWorks, Windows CE. So today we would like to talk about Linux OS. Okay, Unix like RTOS from Linux works mostly used in avionics, aerospace, military, telecommunication. Example of application are Airbus A380 flight test, TLDM's Laksamana class corvettes, HP LaserJet printer. Okay, next we would like to talk about OSE. Okay, and the full form is Operating System Embedded. RTOS created by ENEA AB, ENEA AB. Supports 32 bits processor like ARM Cortex or PowerPC. That powering phone like Nokia, Nokia OS, Sony Ericsson and Motorola. Okay, and the third one is Windows CE, an OS developed by Microsoft for embedded system. Supports Intel x86 and compatibles with ARM processors. Widely used in industries such as retail, manufacturing, health, automotive. Thank you.